Okay, good morning 12 Physics. I'm going to try and record this lesson today because it is a tricky one to try and teach online. So I thought I'd make a separate PowerPoint with this recording in it, and at the end of it I'm going to upload all of the answers onto a separate file on the OLE. And the reason why I've got to do it that way, I can have this file with audio recording, but that makes the file size much bigger. But all of the answers to all of the slides are going to end up online. Now, I must warn you, I've got young children in the house, so they could barge in at any point in time and do something annoying. But with that, let's get started. So I'm on slide 129 right now, torque and equilibrium. So hopefully yesterday you all did the little activity using the FET applet, and you tried to balance a seesaw with putting masses at just the right place. So we're going to be looking at the conditions required to get an object so that it's either stationary or just moving at a constant speed. That's called equilibrium. It's not accelerating. So there are two rules that we can take advantage of. If we know something is in equilibrium, we know that all of the forces acting on the object must add up to zero. So in pretty much every problem you'll do at level 2, it basically means that the whole thing is going to be stationary. But you could balance like a seesaw inside an elevator while it's going upwards at a constant speed. So technically it's just moving at a constant velocity, and that velocity could be zero. But all the problems you'll be looking at are going to involve something that's just stationary. So if it's in equilibrium, the forces add up to zero. So that means all of the forces trying to push the object up have to add up to equal all of the forces trying to push the object down. All of the forces pushing left will balance with all of the forces pushing right, but that basically never comes up at level 2 either. So often people just say forces up equal forces down. And just like what we found yesterday with the seesaw, all of the torques trying to make a beam turn clockwise have to add up to all of the torques trying to make a beam or object spin anti-clockwise. So we can write it as sum of clockwise torque equals the sum of the anti-clockwise torque. And what you do is that you take your equation, and so if you've got multiple clockwise torques, you can have torque 1 plus torque 2. If you've got two things trying to spin like a seesaw clockwise, they would have to add up to the one torque that's trying to turn the beam anti-clockwise. And so then you could go force times distance for the first torque plus force times distance for the second torque, and that must equal force times distance for the anti-clockwise torque. So although our formula is just each torque equals force times distance, we've got to do that for each and every torque, and we've got to set up our equation. So clockwise torques equal anti-clockwise torques. We go force times distance for every one, and make our own formula up that says that these two things must be equal to one another because they are in equilibrium. So to solve equilibrium problems, we've got to pick a pivot. Now at the moment we've only looked at a seesaw, so the natural position to pick for a seesaw is the middle where it's balancing. You then need to draw in all of the forces. So it's like a force diagram, and you have to draw in the arrows showing the direction of the force and how many newtons it is. Then you've got to look at each arrow and think, is that going to make the whole beam or the whole object spin? Is it going to spin clockwise due to that arrow compared to where the pivot is? And which arrows are going to make it spin anti-clockwise? And when we come to clockwise torque equals anti-clockwise torque, then we're going to be able to say, well, that force there is a clockwise torque, so that's going to go on that side of my formula, and this force on the other side would contribute to anti-clockwise torques. So we're going to say clockwise torque equals anti-clockwise torque just to solve the problem. So if we move on to page 131, the first thing we've got to do is we've got to pull out our pen, and we've got to label in all of the forces. So I'm going to put in the weight of the beam, because the beam is 2 kilograms, so weight of beam can go there. I'm also going to put in a support force. And I'm just going to put in I'm going to put in a little point here. I'm going to put in a little star, and I'm going to say I'm going to use that as my pivot point. If you can, you usually want to pick a pivot point, which makes sense. So here I'm going to have weight of 4 kg mass, and so that's going to be for G, where G is our 9.8, and here that is going to have a mystery weight force of mg, where m is the mystery mass. Now you could go through and multiply, each of those by 9.8, so you could have 4 times 9.8 over on the right hand side and 9.8 m on the left hand side. But we'll see that usually it's easier just to leave it as the letter G, because that can often cancel out. So I start off by saying beam is in equilibrium. So the anti-clockwise torque will equal the clockwise torque. So the sum of all the anti-clockwise torques that are trying to make the whole beam tip this way must equal all of the torques which are trying to make the beam tip that way. So we're just going to imagine that these two torques are perfectly balancing each other out. So what we can do is now say, well, the thing that's trying to tip the whole thing anti-clockwise is going to be the mystery mass times gravity. So that's our force that's trying to tip the whole thing anti-clockwise. And I've got to go force times distance. So the distance there is going to be this distance to my pivot point. So I'm going to go 1, 2, 3, 4. In this case, it's 5 meters. So that's going to be times 5. And over here, I'm going to have the force, which was 4g, multiplied by that distance. And I'm going to count out the number of meters from my chosen pivot point. In this case, it's 3 meters. So the reason why I didn't bother calculating g is because I knew I'd be able to cancel it out. So here I've got 5 times the mystery mass equals 4 times 3 is 12. And so I can divide each side by 5 and get that m equals the answer. And that is 2.4 kilograms. And that's how we do a torque equilibrium problem. Now we're going to move on to problems which don't look like they are a seesaw problem, but they really are. It's just that we're going to have 2 of these triangles which appear to support it. And so what we're going to do is we're going to pick one of those triangles to be the pivot point that the whole seesaw is going to be moving around. And the other triangle, we're going to just say, well, forget that triangle's there. We're just going to pretend that it's only a force which is going to try and tip the balance of the whole system. So if we move through, there's some things we're going to skip over. Now here I've actually got the annotated thing. So I've actually got this annotated in here, and I've got the working done, but I felt it's easier to have everyone work through what's there. So here, this one here, this is like the ones that you were doing yesterday. So here we're going to choose a pivot. So I'm just going to put a little mark here. So choose pivot. At that point, beam is in equilibrium. So we can say that the anti-clockwise torque, the torque that's all of the torques that add up to make the whole beam twist anti-clockwise, must equal all of the torques that add up to make the beam twist clockwise. Now, it's very important that we make sure we take all of the information into account. So we've got mass of beam in here. So we've got a few forces that we need to take into account. We've got a 4 kilogram mass, which is pushing down over here. So F equals mg, so that's going to be our mass, which is 4 times gravity. I'm just going to call that g. That's going to give me an anti-clockwise torque because it's to the left of my pivot point and trying to push it downwards. And then out over here, I've got another force. That's the weight of the beam, so that's going to be 2g. And that is trying to pull the entire beam clockwise. Now, we only need to treat the entire weight force of the beam as one force acting through the middle. Just don't worry about the fact that some of the beam is over here and some of the beam is over here as well. You just ignore it. You just keep it simple. Treat the entire beam as this one object whose weight is acting right here. So you don't need to worry about anything else. Trust me, it works out. You could break it up into two masses and have like the weight of this part of the beam is here and the weight of this part of the beam is here. It just makes the problem more complicated and you actually end up with exactly the same answer. So let's keep it simple. So if we've got the weight of the beam, it always acts through the middle. Now we need to have this thing here, and this is going to be put in. So that's going to be 2g. And that one, well, we don't know where that is. So that's going to be at a mystery distance. So let's call that one x. So if we look at it, the force that is going to create an anti-clockwise torque is going to be this one here. I'll just undo that and get the proper color. So that there is going to create an anti-clockwise torque, while over on the other side, these forces are going to create clockwise torques. So that's going to be all of the clockwise torques there, and over here the anti-clockwise torques. So if we go through and we try it, so we can go, the force is going to be mg, so 4g, that's my force, and I'm going to multiply it by my distance to the pivot. So in that case, the distance to the pivot is 2 meters. Over here, I've got 2g for the weight of the beam. That's my weight force, and I'm going to see that's 3 meters to the middle there. So 3 meters plus I've got another 2g, which is this one over here. Oops. Having an issue here. So this one over here is this one here. So that will be multiplied by the mystery distance, which is that x in there. So let's see what we got. 2 4s are 8. Here, I didn't actually need to write meters. So 2g times 3, that's going to be 6g. And then plus 2g times x. Right, so what I want to do is divide everything by g. So these will all just vanish. And that would leave me with 8 equals 6 plus 2x. Now if I subtract 6 from each side, turn that into 2 meters. 2 meters equals 2x. So turns out that x equals 1 meter. So what I actually have to do is I have to put that, based on my algebra, that's telling me that that actually needs to go right there. And if I put the 2 kg there, then the whole beam will work out to be perfectly in equilibrium. Okay, so let's move on and skip past this torque experiment. I can do some online applets and things and stuff, and this one's a bit hard, so we're not going to worry about that one there. So we're going to look at one of these two pivot problems. So this is what the exam problems usually look like. You will be asked, what is one of these support forces here? So the first thing we need to do is go, okay, if this is going to be the pivot, so we can just mark in that we're going to have that thing there. Now imagine that this whole problem will make a lot more sense to you if you imagine the whole thing is just a seesaw like before, and we've got the weight of the beam trying to pull the seesaw that way. We've got the support force over here. It's pushing up at the beam. We've got the 5 kg mass which is pushing down, and then now over here we've got an upwards force, and that upwards force is going to be coming from the triangle support. But if you just imagine the whole thing, it's still a seesaw. Forget about the triangle over here, and just think of that as just being an upwards pull. So if we look at that and we're taking torques about this point here, so if we're taking torques about that point there, then we can recognize that there's going to be, this force here is going to try and twist the whole beam anti-clockwise about that pivot point I've picked. Meanwhile, I've got two forces which are trying to pull the beam clockwise. So it's still a seesaw problem, but we're up to 3 forces now. So what we need to do is we need to figure out what that mystery force is using torque equilibrium. So we can add in the weight of the beam is 19.6 newtons. So we can just go through, we could do it with G if we wanted, but they're just telling us that the weight of the beam is 19.6. We've got the weight of the block, 5 times 9.8 is our 49 newtons. This problem is a bit more complicated than the last one, so I'm just going to have everything done in numbers. This is going to be the support force over here at the pivot point. We'll worry about that later. This here is, well, let's call it F2. We want to find this one. So we want to find that one. So what we're going to do is we're going to say, okay, so the clockwise torques equals the anti-clockwise torques. So the sum of all the torques add up to 0. So all of the clockwise torques equal the anti-clockwise torques about the pivot. So we can take that and go, the clockwise torques, that's going to be due to this one, and due to this one. And the anti-clockwise torques, torque is going to be due to this arrow over here. So that arrow is trying to twist the whole beam anti-clockwise about our pivot. So here's our pivot over here, and the clockwise torques are trying to push the whole beam clockwise about this pivot, which I drew with a blue circle. So once we've got all of that, we can go torque equals force times distance for each of those things. So here we can go force times distance. So over here we've got the force times distance. So here we've got F5 D5. I don't know what we... Oh, so this is the force of the 5 kg. So here we've got the 49 newtons, and we're going to multiply it by a number. And here I'm just pointing out that distance, I'm going to go 1, 2, 3 meters away. See how they've been really sneaky, and they're actually measuring from 1 meter here. So it's the distance from the pivot. So it's 1, 2, 3 meters from the pivot. So that gives me my distance there. And the weight of the beam is the 19.6 newtons, and that's only 2 meters away from my pivot. So both of those that I've all shaded in yellow, those are all trying to twist the whole beam clockwise. And then meanwhile, the anti-clockwise torques turn out to be just that mystery F2, and that's 5 meters away from my pivot. So I've got this algebra expression, and I can go through and I can solve that. And there's probably easier if I do one more line of working in there somewhere. So just to be clear, 49 times 3 is, so that would be this line here. So that's 147 plus 19.6 times 2. That's 39.2. So that equals 5 F2. And so 147 plus 39.2, that works out to be 186.2. So 5 F2 equals 186.2. And we'll divide each side by 5. And that gets me to my 37 and a bit, which is this here. And don't worry if it's, I mean, I just got 37.24. Don't worry if it's not perfect. We're not going to worry about that. Now, I said before that there are two conditions for equilibrium. So the clockwise torques equal the anti-clockwise torques. That's the one that students find hard. Now, the easy one is that the forces up must equal the forces down. So we can go, well, now the forces up, that will be that F1 and F2. They're both trying to push the whole beam upwards, and they must perfectly balance the 49 newtons weight of the big box and the 19.6 newtons weight force of the beam. So that gives us, so the forces up, these forces here must balance out with the downward forces. So I've got these forces going up, and I should use a different color because this is up and down now. This is different. So anyway, the upward force is going to be F1, which we're trying to find out. It's going to be that 37 and a bit newtons. And the downwards forces are going to be 19.6 and 49. So here we solve for F1. So there's a lot to take in. So if we have a go and we want to do one of these, we're going to start from scratch and we're going to just work through one together. So I'm going to calculate the support forces here. So I can put in the forces I know. So that was 19.6 newtons. And this one here, this is going to be downwards. That is our 49 newtons. So remember, we're just imagining the whole thing is still a seesaw. We've got a 49 newtons on the end there. And we've got this mysterious upward push, which we'll call F2, from that support. And we're trying to figure out how big that is. Here we've got 19.6 newtons. Over here we've got F1 acting on the beam, but because it acts through our pivot point, that doesn't create any torque about there. It's like trying to push a door on the hinge. It doesn't move the door about the hinge. So when we do the torque bit, that's going to be ignored. So beam is in equilibrium. So the anti-clockwise torques, we call that clockwise torques. So here the anti-clockwise torque. The anti-clockwise torque is going to be any torque that's trying to tip my seesaw anti-clockwise. And here, that there is trying to move the whole beam anti-clockwise about my chosen pivot point. I'm choosing my pivot point here. So I can write that in. I can write in force times distance. So F2, and how many meters away is it from my pivot? It's going to be 1, 2, 3, 4, 5 meters away. So F2 times 5. that must equal the torques of these other forces. So that's going to be 19.6, force times distance, 19.6 times, so that's going, and that one there is now going to be 2 meters away from the pivot, so it's going to be 2. And I've also got another clockwise torque. So my clockwise torque's everything that's going to try and tip it clockwise. Try and make my seesaw go this way. So these two are my clockwise torques. So I've got to do force times distance for each of those. So 19.6 times 2 meters plus 49 newtons. And that one there is 1, 2, 3, 4, 5 meters away. Once we've got this far, it's just solving the numbers. So 19.6 times 2, 39.2, plus 49 times 5. That's 245. So that's 5 F2. And we'll just sum those together. That's 284.2. I'll divide each side by 5, 56.84. So that's 56.84 newtons up. We can also say, well, now we'll do the other condition for equilibrium. So over here, forces up, equal forces down. So all of the things trying to push that whole beam upwards, it'll be F1. It's trying to push it up, and F2 is trying to push it up. And the force is trying to push it down. It's going to be the 19.6 newtons. And the 49 newtons. But we just figured out that F2 is 56.84. So that has to equal the numbers on the other side. So we'll just sum those. So the mystery force pushing it up is F1 plus 56.84 newtons, which we figured out using the clockwise torque equals the anti-clockwise torque condition. I stuffed that up over there. That should be an arrow going this way. Make it easier. And that means F1. To undo addition, we do subtraction. So 68.6 minus 56.84. That will equal 11.76 newtons. And that's going to be upwards there. So that's one answer, and that's the other answer. Now these are excellence problems. So don't be intimidated by them, because they're just following step by step by step all the way through. This is the most common type of problem. So what I'm going to do is I'm going to stop recording there, but we're going to have this problem there and that problem there, and that's going to be, so slides 142 and 143 have got two problems for you to attempt yourself, and I'm going to put my working and answer up on the OLE. So I want you to attempt it doing the same technique. You got to say the beam is in equilibrium, so the clockwise torques about this pivot equal the anti-clockwise torques about this pivot. You go force times distance and force times distance on each side, and you're just trying to find out what that mystery F2 force is. And once you've done that, you can go forces up equal forces down, and then you can use that equation to figure out what the mystery support force at point 1 will be. And you can do that for both of these problems. And I'm going to put the answers up on the OLE in the usual place. And I will also, I'll probably also put some answers I wrote up last year into this PowerPoint slide, so they're all in the same place as well. So I'm going to stop recording now. And if you've got any questions, you can email me and put them up on the social stream.